Greetings students, today on the 18th of July of 2023, Math 505 evaluated this infinite series using a quick, clever way, and I'm also going to share my approach to the same problem with you. I continue the solution from the point where he applied partial fraction decomposition to the summand and wrote it as half of the series as n runs from 1 to infinity of 1 over 4n plus 1 plus 1 over 4n minus 1 minus 1 over 4n minus 1 over 4n. And I'm going to write these as the sum of two series, each of which is a convergent series. So we have half of the series as n runs from 1 to infinity, and I'm going to get one of these negative 1 over 4 ends with one of the other fractions. So here we have 1 over 4n plus 1 minus 1 over 4n, and the second series again running from 1 to infinity of 1 over 4n minus 1 minus 1 over 4n. And like I said, each of these series is a convergent series, since if you add, for example, these two terms together, you get a second degree in the denominator and a constant term in the numerator. So it's in the order of 1 over n squared, which is convergent from P series. Now I can write each of these summands as an integral, as a definite integral. But before that, since I'm going to use geometric series, first I have to apply a shift of index to both of these series. So I'm going to shift the index such that n starts from 0, and to make up for that, I have to add 1 to n in the sum. So the first summand becomes 1 over 4n plus 5 minus 1 over 4n plus 4. And if I do the same change, index shift to the second series, we get 1 over 4n plus 3 minus 1 over 4n plus 4, all of these times the half. Now I can write each of these summands as a definite integral from 0 to 1 of a dummy variable y. So I can write that 1 over 4n plus 5 as the integral from 0 to 1 of y to the 4n plus 4. Since the antiderivative of y to the 4n plus 4 is y to the 4n plus 5 divided by 4n plus 5. And if you evaluate it from 0 to 1, you get 1 divided by 4n plus 5. And similarly for the other terms, I can write minus y to the 4n plus 3 dy plus series n running from 0 to infinity of the integral from 0 to 1 of y to the 4n plus 2 minus y to the 4n plus 3. If you compare, you notice that all the exponents of y's in the integrand are one less than the terms in the denominator, in case you want to do that quick. And now I can combine these two. So we get half of the series n running from 0 to infinity of the integral from 0 to 1. We have a term of y to the 4n plus 4, and then y to the 4n plus 3 appears twice, so we get negative 2 times y to the 4n plus 3, and then plus y to the 4n plus 2. dy. Now I can swap the order of summation and integration. I know that's very risky, but rest assured, I've made sure that it works. And we get half of the integral from 0 to 1 of the infinite series, all these terms. So now this series are integrand with respect to y. Then we can convert this infinite series to an expression using the result of geometric series. So I have 1/2 times the integral from 0 to 1. I can write the first one as y to the fourth divided by 1 minus y to the fourth. The second term here, that would also have a denominator of 1 minus y to the fourth, so I can combine it here, and we have negative 2 times y cubed. Same thing for the last term, and it will have a y squared. Now we have a rational function in the integrand, and since the orders are the same, we have to do a long division first and then partial fraction decomposition. And I skip over the details because I'm quite sure that you all can do it. And after the long division and partial fraction decomposition, the integrand turns into -1 plus 1 over y plus 1 plus 1 over y squared plus 1. Or sorry, y over y squared plus 1. And all of these terms are quite simple to be integrated. I'm just going to put a 2 here and a 2 down there. And the result of this integral is 1 over 2 times -1. The integral of -1 from 0 to 1 is -1. Then we get natural log of y plus 1 plus half of natural log of y squared plus 1, where in these two y's evaluated from 0 to 1. So we get 1 over 2 times -1 plus natural log of 2 plus half of natural log of 2, which is 1 over 2 times -1 plus 3/2 of natural log of 2, or finally 3/4 of natural log of 2 minus 1 over 2. Okay, great, and we are done. Thank you.